There we go. All right. So we'll start with statistics, and I'm going to assume that y'all have some idea of like statistics and that this is a review. Would I be terribly wrong in making that assumption, Marissa?
No, I think we all have learned or taken everything on statistics.
Good, good, excellent, excellent. So I promise to be nice. I will be nice. If you don't know anything, please ask. And we'll get on with it, right? This is the stuff we're going to do, right? I'm just going to turn on my stupid camcorder brain here, and I'm going to get going with this, right? Now, all measurements have uncertainty, right? So what does that mean, right? Well, here's an example of a glucose meter. My mother-in-law uses one of these, right? It's exactly like this. It has a this is like a piece of, it's a glass cover slip over a little channel, and you've got and they have these lancers, and you stick her finger on the lancer, boom, and this little needle shoots out, and it pops a hole in her finger, and she starts bleeding, you know, not copiously, but a little blood comes out, right? And then you just put the little test kit up to the blood, and it just sucks up in that channel, right? And then it goes, and then it tells you the glucose concentration, right? Now, glucose is an exceedingly difficult molecule to measure unless you have biology on your side, in which case it's pretty damn easy, right? But you need biology. So, so these meters use what's called glucose oxidase. And glucose oxidase, it's an enzyme, and it will latch on to the glucose molecule, and it will trigger its oxidation. And then that's electrochemical, right? And so then suddenly this glucose is going to be giving up electrons to an electrode and making carbon dioxide and other crap, right? And it will tell you a number like 90 mgs per DL, right? 90 milligrams per deciliter. What's a deciliter? What's another name for a deciliter? Who knows? Gentlemen? John? Deciliter? Deciliter is 100 mils, 100 milliliters, right? It's a tenth of a liter, right? See, that's what being a professor tells you. So anyhow, and if you measure replicates, you will likely not get the same value every time, right? Now, in this case, you only get 2 sig figs, 90, 94, 85, 95, 93, right? And the average there is 91.4, right? We added a sig fig when we took the average. I don't know. It's probably a good idea. And in this case, the true value is 99, right? That's measured by some alternate method, some alternate highly accurate method, right? And so what would you say about this measurement relative to the true value of 99? Who wants to, I mean, make an observation here? John.
The accuracy is off. So it's like you measure it with like plus or minus.
Yeah. So the accuracy, to know that the accuracy is off, you look at 99 and 91, right? So the accuracy is off by about 10%, right? It's supposed to be 100, but it's 90, right? So it's 10% low. right? Now, what else about the meter can you say given this bunch of results? Jenna.
The 5 measurements aren't really precise. It's kind
That's
of all over the place.
Exactly. So 85 to 95, that's the range of measurements that we get, right? So we might, if we were to make an estimate of the fluctuation, we might say plus or minus 5, right? That might be a little bit much. Maybe it's plus or minus 3, right? Like, because there's always a possibility of a larger outlier or a smaller one, right? So this measurement of the outliers, it's like a standard deviation thing, and it's so you have to, you look at this range, and the actual standard deviation will be smaller than the total range in most cases, So measurements are never perfectly accurate, and they're never perfectly precise. But you can make judgments about them if you have a measurement that is relatively accurate and relatively precise, right? That's what this 99 is, right? So what we're going for with statistics is we're trying to get to that higher level, right? And the statistics gives us tools to accept conclusions that have a high probability of being correct and reject ones that have a high probability of being incorrect, right? And it also tells you, it's also a tool for telling you what the fluctuation in your value is, the relative and the absolute fluctuations. All righty. So first of all, a Gaussian distribution is what you expect from a real system, right? Well, actually from an ideal system. And I'm not actually sure how the Gaussian distribution was derived, but it's representative of a lot of physical processes, and it's this curve over here, right, that peaks at a mean value x bar and then falls on either side is e to the actually let me well, I can't write on the screen right now, but this is e to the minus z squared, right? Z is the distance from the mean, and z is the distance from the mean in units of standard deviations, right? So e to the minus z squared falls off very quickly, right? So e to the minus a power, right? That's a negative exponential, right? And that falls off fairly quickly, right? But then when you square it, e to the minus z squared falls off even more quickly, right? So the z squared function is a funny thing, right? Because it's kind of blunt. Like if you remember like a parabola that goes up, that's for z squared, right? Now, but right around the bottom, it's fairly blunt, right? So that's what gives this function its bluntness around the top. But then out here, it goes to essentially 0, You can put any number plus or minus into the Gaussian function and get a real value out. You can get a value out, right? But the values that come out of that Gaussian function are mostly going to be zeros, right? It's almost like saying, there is a possibility of all the air molecules in the room going to the left side, but it's just super, super improbable, right? So, you know, that and that type of thing is normally a Gaussian function, right? So you know about Carl Friedrich Gauss? Yes, Kiara? He was an unsung hero of the molecule. He was a big friend of Maxwell. Maxwell did the Maxwell's equations for light. You know, he developed all the equations that describe electric fields for light, electricity and magnetism. You know, and Boltzmann was his big buddy, right? And they got along really well because Maxwell was apparently a really nice guy, and Boltzmann was kind of a sad character, right? Because he believed passionately in molecules, but nobody else believed in him. There was no evidence for molecules at that time. And there was a very stuck-up crowd. Scientists at that time, they were very stuffy and stuck up, and they did not believe Boltzmann. And he eventually ended up, he took his own life because nobody believed him. But just shortly after his death, oh, sure, of course, yeah. I'm trying to live transcribe this. Hopefully that works. But slightly shortly after Boltzmann's death, our good buddy Albert Einstein, he always just interpreted, he never did experiments, you know, real bastard for that. I hate him. But anyway, I love him. But he interpreted, like, there was this thing called Brownian motion, right? Where they looked at tiny little things that are smallest things they could see under microscopes. And if you look at them, they move erratically. And nobody really understood that motion, right? You knew at higher temperatures, they moved more. At lower temperatures, they moved less, right? But it was Albert who figured out that these were molecular motions, they were molecules bumping into things, causing these motions. And he modeled it mathematically and he proved it. Thank you, Albert. It's had nothing to do with relativity, nothing. But anyway, so Gauss was an interesting character, right? He worked with Maxwell on the distribution of the speeds of molecules in a gas, right? So the Maxwell Boltzmann anyway. I have to go back. I'm conflating Boltzmann and Gauss. But anyway, Gauss might have been, no, it was Boltzmann. I'm talking about Boltzmann. Gauss was an older guy. Sorry. That wasn't Gauss, it was Boltzmann. Go back in your brain, erase all that stuff and replace when I said Gauss, replace that with Boltzmann. Oh, well. Anyway, so Gauss, I'm not sure who he was. But the idea that you know, molecular speeds or experimental results will have this e to the minus x squared form is really fundamental to science and chemistry and everything, right? So and what we do as you know, actual experimentalists is that we don't have the luxury of doing everything a gajillion times. You know, this is 20 coin tosses. This is 400 coin tosses, right? And at 20 coin tosses, it's not easy to conclude that this is a Gaussian distribution here, right? That this, forest of results in this histogram is a Gaussian distribution. Now, y'all know what a histogram is? Is that like, gentlemen?
It's like
So.
a bar graph.
Yeah, it's a bar graph. Excellent. Yes. And the y-axis is the number of observations, and the bars have a width. And the width is like, it's like a pachinko game or something, right? Where the marbles come down and they bounce all around, and they all land in a certain well, right? And the well has a width, right? And so these are probably like 1 unit wide, 25.5 to 26.5, 26.5 to 27.5, 27.8.5, 8.5 to 29.5, 29.5 to 30.5. Like, so these are width of about 1, right? So if you pile all the results that fall in that interval into that bin, then the bin gets taller, right? So you notice this 20 tosses, the most they ever saw within a given range was 5, right? So all these guys, they can only differ by 1, right? So this 20 tosses, it's hard to establish the absolute Gaussianness. So what we're going to do mostly is we're going to assume that our results are Gaussian, right? It's not always true. And most likely it won't matter, because we're not going to be delving that deeply into the statistics, but we're going to be using them in a sort of an ugly approximate way. And it's not going to be so like rigorously statistical, which is good for me because I'm not a statistician. But in any case, right here, now here's the 400 tosses. The most they ever saw in any one bin was 45 or 44 here, right? But they're able to say that the mean is 24.98 and the standard deviation is 3.71. Standard deviation is, it's a particular statistic that comes out of the data, right? And so another thing I wanted to mention about this, right, is that if you have all these data right here, let's take this 400 toss data set, right? You know a lot about this experiment, right? This coin toss experiment, right? You know the mean value and you know the standard deviation, right? Now, there's an interesting analogy here, right? And it comes from photography, right? It could be photography of distant planets, or it could be microscopy of tiny things. But they both have a similar limitation, and it's called the diffraction limit, right? And what that means is that if you're looking at a point of light, or let's say you're looking at a disk, right? And that disk gets further and further and further away, right? Then what will happen is that disk will get smaller and smaller to a point. And then, even though it's getting further away, it will remain the same size. It will. Trust me on this. It gets smaller and smaller, and then it becomes a point. right? That's why we can see distant stars, right? Because they shrink to their diffraction limit and then they look the same size. I mean, they're super, 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 super bright, right? But still their size gets to a minimum point and then it stays, right? The same thing is true in microscopes, right? As you look at smaller and smaller things with light, and even the smallest damn things look the same size. Like if you have a single atom that's emitting photons like crazy, if you got a single atom in an optical trap or something and it's pouring out photons, if you look at that with a microscope, the damn thing looks like it's 150 nanometers wide, right? And it's not, right? But if you look at it carefully, it produces a pattern that is Gaussian in nature, or Lorentzian. There's a closely related form called Lorentzian, right? But the thing about it is that it produces a pattern like this, right? Now, up until about 5 years ago, microscopists were basically defeatists about this. They say, no, you can't see any detail beyond 150 nanometers in an optical image because that's the diffraction limit, right? What they were ignoring is that you can know the point from which this light emanates, right? If you have a field of points, they all have the same goddamn standard deviation because they're all like emitting molecules or something, right? So they look fat, but they're actually, but you know they're small. Then what you can do is you can just analyze the data that comes out. And if you get enough photons from every point, you can say, no, that's not here. It's right in the middle of that distribution of points, right? And that's called super resolution imaging. And that shit works. And they got the Nobel goddamn prize for that. There's a few guys from Stanford and a few other folks, and they got the Nobel Prize for super resolution imaging. And basically, there's a technique called Fourier transform you can do to images, and you basically you look at the peaks in the Fourier distribution, and you filter off those peaks, and you can see, and then you reproduce the image, and you can see the details of where stuff are in great detail. Good out by a factor of 10. All right. So anyway, Gaussian distributions are typical of physical measurements that we might make. I do not have a clock. I'm probably, it's 6:36. Okay. All right. So y'all know how to do this, BFD. Precision and accuracy, you know these definitions. Now, the degrees of freedom is a slippery subject. For averages, it's always n-1. If you do least squares analysis and you fit to a line, you get two parameters out, slope and intercept. And the degrees of freedom in those two statistics that come out is n-2. If you do 3 parameter fits, it's n-3, etc. Right? And I'm not going to talk much more about that because I'm going to get in trouble. But now the variance is a squared standard deviation. Okay, big deal there. The relative standard deviation is something you should know about. That's 100 times standard deviation divided by the mean. So when you reduce the standard deviation this way by dividing it by the mean, you get an idea of a measurement standard deviation relative to its magnitude, right? So if you ever done, if remember back from organic, you did NMR. You guys remember that? Maybe. Well, NMR tells you the position of a peak in parts per million relative to a standard ppm, right? Now, in that case, the peaks are extremely sharp, because within a fraction of a part per million, you can know their position, right? So they have a very small relative standard deviation. And the absolute deviations are very small. Okay, so we're not going to do this shit. You guys have already done this. You're going to use a calculator. Okay, so you can use a spreadsheet, right? Take an average, standard deviation, right? So if you have any interest, if you have any need for reviewing this stuff, I'm happy to go over it with you. I just don't want to take the class time right now because many of you, or maybe there's a show of hands. How many of you are good with spreadsheets? No? Yes? Okay, all right. I'm getting okay, all right. But you can, okay, so you're gonna learn it anyway. It's gonna come back and back and back. So hopefully you can be good with this. But you know, the idea in a spreadsheet is the cell contains the text equals stdev.s, open paren, the argument here are cell addresses, B1 to B4 is like these guys, you know, and then what happens is when you hit enter, then instead of seeing this, you see the actual computation, right? So anyway, we can do that again. There's the formula for the standard deviation, right? Or for the Gaussian distribution, right? X minus mu e to the minus x squared over 2 sigma squared, right? So in X space, this declines as e to the minus x squared, right? Now there is a way that one can reduce experimental values all into a universal curve, right? That centers on 0 and branches out in units of z, and z is x minus mu over sigma, or x minus x bar over s, right? Mu is the population mean, the true value. X bar is your best estimate of the population mean. Sigma is the population standard deviation, and S is your best estimate of the population standard deviation, you know, with a limited data set, right? Now, we can do some experiments with that. And you can calculate, there are some useful calculations you can do if you know X bar and mu, right? If you know X bar and mu, you can calculate the probability of making an observation within a given range, right? So what is the range, that is the mathematical range of probability? What is its minimum and maximum value? Wait, Jeffrey Perez. Yes. What is the range of probability? Probability varies from a minimum of to a maximum of. Snigdha.
If it's stupid, I'm sorry, but is it 0 to 100?
It is not stupid. No need to apologize. It's 0 to 1. 100%. If it's percent, it's 100. But 0 to 1 is the normal way we say it, right? So, so the area under a Gaussian curve, if it's a probability, should be 1, right? That would be a normalized Gaussian curve, right? So that's good. Good. Yeah, so I'm not sure, like, you guys say this is all old hat to you. I'm not so sure. That's an important point, though. Probabilities maximum is 1, right? So, okay. So you can learn how to do this, and you can learn how to do norm dist, right? And you give the mean and the standard deviation, and you can get the area from minus infinity to a value by saying norm.dist, right? Minus infinity, what the hell is that? Well, that just means that value or less, right? What's the value of me weighing, 200 pounds or less, right? If you know my weight, so what's the value? What's the probability of my weight coming out to 200 pounds or less, right? You go, oh, well, maybe, 10%, Then you can say, what's the value of making a measurement of my weight and getting between 200 and 210, right? And you would just put in my mean weight, which is probably 215, and the standard deviation is probably 5, right? And then you can plug in this formula and get the answer out. So let me see if I can get this. Let's see here. Here, let me try this out, right? So you can say, like, if there's let's say that my mean weight, my weight is 215 and the standard deviation is 5 pounds, you got a really crappy scale, right? And say, what is the probability of getting a weight of 205 here, right? Oh my god, 0.5. Oh wait, no, that's 215. 205, right? 0.02, right? So being off by 10, there's only a probability of 0.02 is the probability of making a measurement between minus infinity and 205. That's what that is, right? And we can say 220, right? And the probability of making a measurement between minus 15 and plus 220 for me is 0.84, right? Let's call this 210, right? 15% to 85%. So between these two limits, between the mean and plus or minus the standard deviation, there's a 68% probability of finding my actual weight, right? I'm going to put in the formula text. Oops. Formula text of that guy there. That'll show you what's in that cell. And I'll drag that guy down so you can see. Oops, no, not like that. There we go. So anyway, this is Excel. I can go on and on about that. All right, so we'll try to get through some of these in the homework, right? But what I would like to talk to you about is let's go back to this idea of appropriately finding the mean, right? I was telling you how if you have a lot of data, you can identify the maximum point in a distribution. The more data you have, the more closely you can estimate where that distribution is, right? And the closeness varies as the square root of the number of observations or the number of measurements, right? So the standard deviation of the mean is what we're talking about here, and that is equal to S sub x, standard deviation of the measurements, which is representative of the width of the curve, divided by the square root of n, right? And that value is your best estimate of what you know, the mean actual, or what the mean value actually is, improves as 1 over the square root of n, right? Now, okay, so I have to just basically leave that there. And now let's go on. We're going to go into a couple of types of statistical tests, right? And we're going to be moving from our familiar units into universal units, right? The first thing we have to do is we have to be able to take two measurements and say, are their standard deviations approximately the same, right? And there is a statistic that tells you that, and that is called F, or the F test, right? And when you talk about statistics, you start with what's called the null hypothesis. And the null hypothesis means, hold on, we cannot distinguish these populations, right? We can't distinguish the means, and we can't distinguish the standard deviations. Everything is the same. Stop measuring, right? Or, you know, or measure more, right? If you want to see a difference, right? And the differences that you see are only from random variations. And you need to reject the null hypothesis only if there's a less than 5% probability of observing the experimental results that you do, that you actually are observing now, if the two populations are identical, right? So if you take an identical population, you measure it 5 times, then you look away, then you look back, you measure it 5 times again, you will not get, none of the observations will be the same, right? But one of the statistical tests that we're gonna measure is like, what is the probability that we see, or what is the probability that these two sets of observations can come from the same data set, right? And it comes out as a percent probability, and it's a percent probability that the experiments come from populations, identical populations, right? So anyway, let's move forward here. I kind of botched that a little, I muddled that up a little bit, I know that, but I got to move forward because I'll get us stuck, right? So the two tests we're going to learn are the F test and the T test. And I learned the T test first and then the F test, but Harris teaches the F test first because the F test, you need to pass the F test before you can do the T test. So the F test compares the standard deviations, right? So you've got two populations and you ask yourself, what are the standard deviations the same or different? And the T test says, well, if you pass the F test, are the two means different, right? So the F test is calculated by taking the ratio of the standard deviations, and squaring them, or taking the square of the ratio, right? And here you get, you can flip this around, right, any way you want, but you need to flip it such that F is greater than 1, right? So S2 is the smaller of the two, and S1 is the greater of the two, and you take that ratio, you square it. And then you look on a table, right? Once you've taken those two S values, you squared them, you ratioed them, then that is an F calculated value, and that F calculated value does not have units, right? You cancel the units when you do this. And you move from units of pounds or, milligrams or whatever, volts or whatever, you move that to a universal, unitless world. And in this case, that world is F, right? And you can take this value of F and compare it to a universal value of F. And you can conclude based on that whether or not two populations are the same, whether the two S values are statistically different, right? Now, how would you do that, right? Well, here's an example. It involves horses. I don't know why. I think Dr. Harris must bet on horses. Crazy guy. Anyways, so bicarb, you can inject, you can juice your horse with bicarb. Isn't that crazy? And I don't think it's good for the horse, but it gives us some short-term ability to work harder, right? To not get tired as quickly, right? And if you made 10 measurements with your original bicarb instrument and you got a mean of 36.14 millimolar and a standard deviation of 0.28, then you got a new instrument and it gave you 36.2, a mean of 0.47 with 4 measurements. Can you state whether or not these are the same or these are the same, right? We start with a standard deviation, right? Now, so in order to do this, we'd take 0.47 over 0.28, right? And we're going to square these two guys. Whoops, let's see here. 0.47 squared over 0.28 squared is 2.8, right? And what we're going to do is we're going to go to the F table and we're going to look at the 3 and 9 degree of freedom points, right? That's because this has 4 measurements and 3 degrees of freedom. This has 10 measurements and 9 degrees of freedom, right? So something to keep in mind here is that the smaller value has more degrees of freedom. So that will be the second one that we do. And now we're going to go to 4 and 9. And that guy gives us 4.72. Oh gosh, this is a little bit complicated for me sometimes, right? Because there's a couple ways to F it up. One way, because you've got 2 numbers, right? And you've got 2 degrees of freedom. And the smaller one goes on the bottom, and that is S2. And S2 has this higher degree of freedom, right? And S1 has this lower degree of freedom because it's a larger one. So anyway, we go through all this work and we find that 4.72 is our universal F value, right? Now, what does this friggin' mean? This means that this is all positive, they're all positive values, because when you square them, they're positive, right? And standard deviations are always positive anyway. And so the minimum value for a ratio of standard deviations is 1. And then this minimum is 1, and then they go up from 1. Right? And so for that combination of 9 degrees of freedom and 4 degrees of freedom, the the 95 times out of 100, the same population will give a ratio of 4.72 or less. I just said a mouthful. So, and I am so shitty at teaching this. Literally, I suck at it. And I don't know how to do better. So let's do an example. Let's just do this stupid example here, right? Maybe I can dig myself out of this stupid hole, right? We got 36.14 plus minus 28, 10 measurements, and 36.2, 0.47 and 4 measurements. So this standard deviation is larger. So this is going to be S2, right? Oops, no, this is S1. The larger one is S1, right? And S1 over S2 is a number greater than 1, 2.8, right? And F table, 5.08. What? 5.08. It's 4 and 9, right? 4 and 9. Where are we? 5.08.
It's
Oh,
3 and 9.
3 and 9. 3 and 9. See, I suck at this, right? So 3 and 9 is 5.08, right? And then we look at our actual data, and for this, all 6 of these data points boil down to 5.08, right? And our experimental variance here is 2.8, and our F calculated is less than F table. So we say no evidence that these are different, right? Because if these were larger, if this was a huge difference, then they would be greater than the tabulated value. Then F calculated would be greater than F tabulated, right? That's the way that works, right? Now I'm gonna jump on this opportunity, and we're gonna talk about a similar thing, which is confidence intervals, right? And here we're going to calculate t values. Now, let me give you a let's do a comparison of means here. I'm on a roll here. Come on, Roger. Don't screw it up. Here's a t calculated, right? We did an F calculated, was ratioing standard deviations. Here's a t calculated, and this compares means, mean values, the mean of population 1 and the mean of population 2. What's your puppy's name, Kiara?
Her name's Nala.
Nala? Nala? Puppy? Oh, she likes you. She doesn't like me. Hello, Nala. Hello, Nala. Hello. Hello, Nala. I got her ears to perk up a little bit. You made her say hi. I love it. I love it. Okay. So we got an F calculated from 6 numbers, right? A mean and a standard deviation and a number of data points. We're going to get a mean, a standard deviation, and a number of measurements for X1 and X2. Same deal here, right? Now, if the standard deviations are the same, like they're not distinct by the F test, then we can get a t calculated in this way, right? X, difference in X, notice the absolute value here, divided by S, no more units. S has units. Standard deviation has units, right? X bar divided by S, no more units, right? then you multiply by this weird ass square rooty thing, right? Which is really just a little bit larger or a little bit smaller, I forget. It's slightly larger, I think, than the square root of like the average of the n values, right? So this is the number of points in population 1, the number of points in population 2, you know? And so this is called the reduced degrees of freedom here, I think. And then so you got the difference divided by s, and this gives you a value called t, right? And t tells you, t is from a table, or you can calculate it, right? And t tells you, do the means differ, do the mean values differ? That is more like what we're after, right? When you want to say, like, this swimming pool has too much chlorine, or this person was poisoned by arsenic, or whatever you want to say, it very often boils down to a t value, right? And the t is universal because, Marissa, why is t universal? That's a stupidly unfair question.
It's okay. Yeah, I'm not exactly sure why it's universal.
Okay, all right. So here's my stupid answer. Because you divide by s, right? It's the difference divided by the standard deviation, right? It's the difference relative to that standard deviation, right? So let me give you an example. We're going to do HPLC of Diet Coke, right? And when we do this experiment, we're going to get we're going to have an expected value here, right? It's going to be 45 milligrams, right? Then we're going to have our experimental value, which may be 35, right? And 35 and 45 seem really different, right? I mean, they're really different. But if your standard deviation is 50, they're not different. Right? If you get a difference of 50, but your measurements are so far all over the place, all over the map, you divide by 50, 10 divided, that's 1/5, right? And that is not a significant difference. See, when you divide by s, you place it on this new domain that is t or z. T is actually better than z because T came from a beer drinker. Came from a guy named Stott or something who went under the pseudonym Student. He published his work while he was working for the Guinness Brewery in England. Strutt, I think. I'm sorry, I forget your name, Student. But he developed this statistical test in the mid 1800s, right? And it's just by taking the difference between the values, dividing by the standard deviation, then multiplying by the square root of n, right? So now t, if you have a ton of measurements, let's say n1 is 100, n2 is 100, right? Right? Then the square root of this is going to be like close to 100, right? Now your t values are going to tend to be very large, right? Because whatever difference relative to s that you get, you're going to multiply that by 100, right? That's because when you make a ton of measurements, you magnify your ability to detect difference. T is like difference on a universal scale, on a Gaussian scale, universal Gaussian scale, right? Anyway, I'm going to let you guys do some homework problems here. Are there any questions that I can help anybody with? Or here, let's look real quickly at Lord Rayleigh's data, right? This is just one example, and then I'm going to let you guys go. Just hang in there for 2 more minutes, and we'll go over this, right? This down here is a number line, 2.295 to 2.315, right? 2.3, 2.31, right? These data here are from the fraction of nitrogen in air. Oh, I'm sorry. It's the mass of nitrogen that was chemically generated, right? And this is the mass of nitrogen in air, right? They took all the oxygen out of air and they weighed it, they got 2.31 grams. They took then they chemically generated nitrogen, the same volume, and they got 2.30 grams, right? Now there's a difference here, right? Ostensibly, these are all nitrogen, but the same volume has a slightly different mass, right? Now, the difference is that air has 1% argon. That's a lot of friggin' argon. That's cool, I think. We're really lucky. We got lots of argon in our... Gentlemen, how are you doing? I haven't asked you a single question.
You've asked me a couple.
Oh, I have? Okay. Shut up, Roger. Okay, so now, do you think that these data are statistically distinguishable, gentlemen? 2.31 and 2.30.
I mean, just looking at the numbers, they're really, really similar.
Yes.
Yes.
So you think you can't tell the difference between this population and this population?
I mean, looking at the number line, seeing how they are separated, I guess I could see it just visually. But if I were to just get like the 2 sets of numbers, I don't think I'd be able to know.
Right. If you look at these values over here, they all look, God, they look so similar, right? But when you plot them on a number line, you see that these guys are all bunched up down here, and these guys are all bunched up here. So would you call me crazy if I said that the air had 1% argon? I mean, I don't know. You could call me crazy if you want. Kiara, would you call me crazy?
No, not quite.
Okay. All right. Give me a pass here. Give me a pass. Snigdha, opine, please. Are these numbers, is this population different from this population?
I think I would have to agree with what Jen said before about how they look very different seeing from a number line, but not if you actually look. If you were given 2.300 and 2.310, you wouldn't notice that big of a difference.
Right, you wouldn't notice. But if you divide them by the standard deviation, you get an enormous t-value. And the likelihood that these come from the same population is pretty much 0. Right? because you can get a standard deviation from this, and that predicts a Gaussian distribution of these measurements that just crashes. It's zero out here. It's zero. There's no way that this is going to produce a value of 2.30. Never. Not in a billion years, right? Or maybe in a billion years, right? And this guy here, it's broader, but it's crashing down by the time it gets out here. I mean, we're talking 10 to the minus 12, right? And this T statistic here comes out to 12 for that pair of data sets. And that is the take home message, right? So you guys can do this for this, and then you get like, I don't know. You got to do all this shit, but basically it comes out to like, you get the T calculator comes out to 20, sorry. So it's crazy. Anyway, alrighty guys. So whom will I see on our first lab meeting, Duncan Hall 10, next Wednesday? Excellent. Okay, good. I look forward to seeing you there. We're gonna do some UV Viz. I'll think about whether or not we're gonna do lockers, all that good stuff. Okay, guys. Have a great night.
So
And-
if we have,
yes. Mhm.
sorry,
Yeah,
if
no, go
we
ahead.
have lab on Tuesdays, that's not going to be next week, right? That's going to be the week after.
Right.
Okay.
Right. Yes, you're gonna be the third lab section.
Okay, thank you.
Okay, cool. Great. Bye-bye, everybody.
Have a good night.
Have a good night.
I had one more question.
Oh, yeah.
For the Macmillan learning, do we have an access code for that?
I don't know.
All right.
They don't tell me anything.
For sure.
Go to the website, try to do the homework. And what happens is they let you in on a trial basis and then you have to pay eventually. So I hate making you pay for it, but I kind of have to do it right now. So sorry.
Gotcha. Okay.
Okay, good.
you.
Okay, thank you guys. Oh, no online lab. No online lab tomorrow.